Hey everyone, welcome into lecture number 17 of differential equations. This lecture is an introduction to Laplace transforms. So let's start with a very brief review of improper integrals. In general, if you need to review improper integrals, please do so on your own. You can use your Calculus 2 text, or there is a brief review in our textbook. But improper integrals, so what we would like to do, so again, review these on your own if necessary, so be honest with yourself if you remember improper integrals or not. But what we would like to review just very briefly here, basically all I'm going to do is write down the definition of a type 1 improper integral, because those are the type that we're going to be most focused on in this lecture and in dealing with Laplace transforms. So a type 1 improper integral is an integral of the form integral from a, so some constant, to infinity, f of t dt, and in this case the infinity is what makes this improper. And remember that the definition of this is that the limit, this is equal to the limit as x approaches infinity of the finite integral from a to x of f of t dt. Okay, so and of course whenever you define something by a limit you have to say provided the limit exists. Now, when the limit does exist, the integral is said to be convergent, and when the limit does not exist, the integral is said to be divergent. Okay? So, like I said, that's all I'm going to do for improper integrals. I'm just going to remind us of this definition, and we will use this definition in later on in this lecture. But if you do not remember improper integrals, and if this doesn't even look familiar to you, please pause the video now, go back, grab your Calculus 2 textbook, and look up improper integrals in there. All right, but moving forward now, what we want to study in this lecture as it pertains to differential equations are integral transforms. Now we're going to study one integral transform in particular, but I think it's useful to write down a general definition of an integral transform. So a function, in this case, that's going to take in, so a function of functions is sometimes called an operator, sometimes it's called a transform. In this case, we're going to call it a transform. But a function, which I'll call cursive I here, which takes in a function, which I'll just write as smooth function here, c infinity. Doesn't have to be, it could just be continuous, honestly. But for the sake of this, let's just say it takes in a nice smooth function and returns another smooth function on an interval from a to b. If this is given by the form, so a function of the form I of f is equal to some integral from a to b of a function k of st times f of t dt. All right, this is called an integral transform. An integral transform. All right, so this kind of function is called an integral transform. And the whole idea here is that this integral transform takes in a function and it returns a function. Well, how does it return a function? This is a definite integral, right, from a to b. The way that it returns a function is that in this function k of st, there's another variable. There's a variable s here, right? So actually the output here, the I of f, this is a function whose variable, whose independent variable is s. So I of f is a function of s in this scenario. All right, it's a function of s. Now this function k of st, so k, the function k, whose variables are s and t, this is called the kernel of the transformation. So that's why it's called k, right? K for kernel. So this is the kernel of the integral transformation I. All right, or the transform I. So, like I said, this is a general definition, and as you move on, as you go on in your studies, and especially if you're in engineering, there are different types of transforms. There are Fourier transforms, which you'll probably use extensively, and there are a number of other integral transforms. There's all kinds of integral transforms that you will study. In this course, we are only going to study, or at least in this chapter, we are only going to study the Laplace transform. So we need to give the definition of that now, right? So the Laplace transform is exactly one of these. What do we need to define our integral transform? Well, we have to define the a and the b, so the boundaries of the integral, and we have to define the kernel, this kernel function, k of st. So I'm going to just write the formula, and then we'll identify what parts are what, right? But the Laplace transform of a function f, so a function lowercase f, is given by, it's going to be another function, right? But it's given by the following formula. So the output function, we're going to call it capital F. It's going to be a function of s, just like we saw up here. The output is a function of s, right? This is going to be another way that we're going to write this is like a cursive L for Laplace applied to f of t. So this is just notation for how we're going to denote that we are taking the Laplace transform of f. It's not yet a definition, right? We don't know how to do it yet. But now the next equal sign, this is going to give us the definition. So it's the integral from 0 to infinity of e to the minus st times f of t dt. That's the Laplace transform. Okay? So if we compare with our just generic integral transform formula up here, we can see, right, how all the pieces match up. Well, the lower bound a, that's constant 0. The upper bound b, that's infinity, so that makes the Laplace transform an improper integral. And then the kernel, k of st, for the Laplace transform is this function e to the minus st. And then the f of t dt, that's the rest of it, right? So that's just what makes it an integral transform. Then we're integrating a kernel function times f. All right? Now, we want to be sure that this transform is going to always give us an answer. So I'm going to put a box around this because this is our definition, right? And in a few moments here, after I write down the next thing, after I write down the theorem, I'm just going to do some examples. So this is really just an introduction to the Laplace transform. And to end this lecture, like I said, what we'll do is just compute some Laplace transforms, and then in the next lecture, we'll talk about how to use them to solve differential equations. So before I do the examples, though, I want to write down an existence theorem. I'm not going to prove this theorem. You can prove it as a recommended exercise if you wish to, but this is going to be an existence theorem for the Laplace transform. So whenever we try to use a new tool to solve new problems, we need to make sure that that tool is going to work, right? And so that's what this theorem is going to tell us. And like I said, I'm going to state it without proof here. There is conversation in the text about how to prove it, and there are some exercises that kind of lead you in the right direction of how to prove it. But here's what the theorem says. It says, suppose that we have two properties here. So number one, that f is a piecewise continuous function. So that means that it doesn't even have to be continuous. Oops, piecewise. But that the points of discontinuity are just single points that are, jumps or holes only, right? So f is a piecewise continuous function on an interval from 0 to a for every positive a, or for any positive a. All right, so in other words, we can represent f as a piecewise, so we don't represent it. F is a continuous function, piecewise continuous function on any finite interval that we choose that starts at 0 and goes to a. So a here in your mind, remember, we know what we're going to do, right? We're going to take a limit here to compute our improper integral. So you think of a as being just a very large number, and then you're going to take the limit as a goes to infinity. So you want to make sure that f is piecewise continuous on every interval that extends in that direction, right, toward infinity. All right, and so the second assumption that we need to make is that there exists, and this is very technical, and this is why we're going to skip the proof actually, because the technicalities I don't think are going to contribute to us understanding exactly what's happening. But let's say there exist real constants. In this case, we'll call the constants k, capital K, lowercase a, and capital M, with k and m both positive. All right, a doesn't have to be positive, but k and m have to be positive, and such that the following inequality is satisfied. So the absolute value of f of t is less than or equal to the constant, it's constant k, right, times the function e to the at whenever t is greater than or equal to m. So basically what this says is that the function f is bounded by an exponential function. So the function f is bounded by this exponential function e to the at times some constant k. All right, so all this does is then restrict the growth of the function as t approaches infinity, right? E to the at in this case, grows very fast itself as t approaches infinity. depending on the constant a, right? But in general, e to the t grows very fast as t approaches infinity. So again, we're looking at this improper integral as t is going to approach infinity. So all we're saying is that f grows less than exponentially, right? Less than exponentially as t approaches infinity. That is a restriction, but it's not a huge restriction. So we'll see that most of the functions that we care about are going to obey this property. Okay? Now, here's our conclusion. Then the Laplace transform of this function little f, so the Laplace transform, which we'll call L of f of t, this is our notation from up there, right? Which we can say also equals just capital F of s, exists. So this Laplace transform exists for s greater than a. Remember, s is the independent variable of the transformed function, right? S is the independent variable of the transformed function, and so the domain of the transformed function is related to the exponent in the bounding function up here, e to the at. Okay, so it's got to be bigger than the bounding exponent. Okay, so this is our existence theorem. Like I said, we're not going to prove this one, but what this one tells us, though, is that it's not a waste of our time to try to compute these Laplace transforms, and that actually, while this is restrictive, it's not super restrictive. So there are a whole bunch of functions that we care about that obey this property, and therefore the Laplace transform is going to be useful for us to actually solve, to solve differential equations, which again we won't do till the next lecture. So what we'd like to do to end this lecture is just take the Laplace transform of a couple of functions that, you know, just to see how it works mostly, but then these should be functions that we see again in our differential equations. So examples. So first of all, I want to take the Laplace transform of just a constant 1. When I write the constant 1 here, I'm thinking of 1 as the constant function 1. So it's the function which takes in any real number, right? Its domain is all real numbers, and it always returns 1. It returns 1 as the output. All right, so let's compute the Laplace transform of 1 based on our definition, or using our definition. So according to our definition, we need to integrate from 0 to infinity, right? Integrate from 0 to infinity. The kernel function, e to the minus st, the minus is very important, e to the minus st, times the function 1, right? The constant function 1, dt, all right? And we need to use the definition from back up here of the improper integral. So we have to treat the improper integral properly, right? So we have to make sure that we use this limit definition to actually compute this. So this will be the limit as x approaches infinity of the finite integral from 0 to x, e to the minus st dt. The 1 is just constant, so we multiply by 1, and we're left with this. We know how to compute this integral, right? In this scenario, s is not the variable of integration, so we can just treat it like a constant, and it just behaves just like a constant, right? So the antiderivative of e to the minus st is negative 1 over s, e to the minus st, and then we plug in our boundaries for t. So t goes from 0 to x. Again, t is the variable of integration. That's why we're plugging in the boundaries for t. And then at this point, we plug in those boundaries before we compute the limit, right? Make sure everything's plugged in before we compute the limit. And what do we get? Well, because of this minus sign, I'm going to kind of switch the order here. I'm going to plug in this one first and then subtract this one and then change the minus sign. So what we end up with is when t is 0, this is just 1, right? So this ends up being 1 over s minus 1 over s e to the minus s times x. Okay, and now we need to take the limit. So the limit is not going to care about this first term because the limit is only in terms of x. It's only operating on the x variable. So this first limit will be 1 over s. It's a limit of a constant, right? Minus this 1 over s can come out, and this one will be the limit as x approaches infinity, e to the minus s times x. And the question now becomes, number 1, does this limit converge? And number 2, if it does converge sometimes, for what values of s does it converge? So basically right now what we're going to do is we are going to figure out, in some sense, the a, right here, the a in our theorem. It's going to come out of our computation, right? So we don't even need to know the a beforehand because our computation is going to tell us the domain. Remember up here, this a is related to the domain of our transformed function, right? Domain of our transformed function. So when you look at this limit here, e to the minus sx, if s is positive, right? If s is positive, then this is e to a negative exponent, right? So I'm going to write this in red. But if s is greater than 0, then this limit, as x approaches infinity, e to the minus sx, this limit is the limit of e to a negative power at this point, because x is positive, but s is also positive, so the minus sign rules here, right? And the limit is equal to 0, right? What about if s is negative? If s is negative, right? So if s is less than 0, then the limit as x approaches infinity, right, of e to the minus sx. Well, x is positive. If s is negative, it's going to flip this sign. And now we're going to be taking the limit as x approaches infinity of e to a positive exponent that's growing. Well, as we just talked about this actually, right? As x gets bigger, e to the x gets a lot bigger. So this is going to blow up and this is going to diverge, right? That limit is going to equal plus infinity. So it's going to diverge. And so what we find then is that, and then if x equals 0, then of course, sorry, if s equals 0, then this term's not even here, but s can't equal 0 because look at the rest of this has a 1 over s, right? So s is not equal to 0, and partially because 1 over s is undefined, right, at 0. And so basically, from all this analysis, and we're not going to do this for every one, but I just wanted to work this out for this one, but for all this analysis, what we've learned then is that the domain of our transform is this: s is greater than 0, because when s is equal to 0, none of it makes sense. When s is less than 0, the limit diverges, right? And so therefore that we don't get a function back. So we only have that our domain of our transformed function is s greater than 0, and when s is greater than 0, this whole term, the limit is 0, so it's gone, right? And so after all this analysis, what we find then is that the Laplace transform of a constant 1 is equal to 1 over s for s greater than 0. So the domain of our transform function is s greater than 0, and that tells us that back in our theorem, the a would be 0, right? The a would be 0. Our function grows less than constant, less than or equal to constant, and that's no surprise because look at, our function is a constant. So we could have figured it out ahead of time. But the point here is that we got it from the limit, right? So that's going to happen in our next couple examples as well. All right, I'm going to put a box around this because we don't want to forget these. So the Laplace transform of 1 is always going to be 1 over s. We don't need to compute this 100 times, right? Once we know it, we can just use this fact that we've worked out, right, to compute to use in later applications. So here's our second example. This time I want to find the Laplace transform of t, right, of just t. Okay, so for this one, same deal. We'll plug in, I'm not going to spend as much time on this, but we plug into our definition. So it's an integral from 0 to infinity of e to the minus st times t dt. I'm going to plug in our limit definition. The limit as x approaches infinity. Integral from 0 to x. I'm going to change the order of this just so we see how this works. All right. And now at this point, this has to be integrated by parts, right? So in this scenario, this function right here is our u, if we do the u dv method here, and this portion is our dv, and so we can just make a little table over here. U, so our u function is t. Well, here, let me just make this table a little bit better. So our u is t, that means our du is just dt, and then with this one, our dv is e to the minus st dt. We just integrated this one, right? So v is going to be equal to minus 1 over s e to the minus st, right? And so at this point, we work out our integration by parts. Remember, whenever you do these improper integrals, you need to do the integral first and then deal with the limit. But u times v minus integral of v du. That's what we're working on, right? So this is going to be minus t over s e to the minus st minus a negative. So plus the integral from 0 to x of negative 1 over s e to the minus st dt. And then we still have to integrate this one again, right? But this one is, again, we know how to integrate e to the minus st dt. So this one's going to be ready to go. And so this is then the limit as x approaches infinity of minus t over s e to the minus st. And then the integral of this one is going to be plus 1 over s squared, right? 1 over s squared e to the minus st. So you get another minus 1 over s term that comes down. And then all of this, we need to plug in our t equal to 0 and to x. All right, 0 into x before we take our limit. And so we have our limit as x approaches infinity. When t is equal, I'm going to do the same thing where I kind of switch the order here, right? When t is equal to 0, this one is 0. This one is going to be minus 1 over s squared, because I'm flipping the order here, right? So that's where the minus comes from. And then when we plug in x, what's going to happen? Again, change the signs and everything. So this one's going to be plus x over s. Let me write it this way. So 1 over s times x e to the minus sx minus so this one is negative. See, I've got myself confused here. This one is negative and this one is positive, then 1 over s squared e to the minus sx. And it's the same deal, right? So now we can take the limit. Again, this is a constant. So the constant here term is minus 1 over s squared. The rest of this, though, is the limits that depend on x. And so just like we did before, we can go through the different ideas or the different cases of what the value of s is. So we can factor out these s terms and just focus on the limit as x approaches infinity of these terms. And when s is greater than 0, both of these are going to converge to 0. And for this one, you can use L'Hopital's rule. I'm going to let you guys do that, but you can work this out. If s is greater than 0, then this limit will converge to 0. Same thing with this. This is the same one we just did, right? These constants make it, or these terms, 1 over s squared, etc., those make it so that s can't be 0. And then, again, if s is negative, then these limits blow up, right? So this is our answer. So all of this stuff goes to 0 if s is greater than 0. Okay? And so what we get then is that our Laplace transform of the function t is equal to negative 1 over s squared for s greater than 0 again. All right? So it's pretty much very, very similar to the first one. So now before I continue, I'm sure most of you noticed that I made a very grave mistake here. I made an awful, unforgivable actually, mistake here. To get this sign is wrong, right? Because actually, what did I do wrong? The integral of u dv in the integration by parts formula is u times v minus the integral of v du. I was going too fast here, and when I plugged in, the minus sign from this one would cancel with the minus sign from this one, and so this sign right here, I'll write it in red, this sign should be plus, right? Which means that actually this sign should be minus, and that changes the signs on this and on this. It doesn't change anything here because that limit's going to be the same, right? But our answer here should be positive 1 over s squared. So I apologize for that mistake. Hopefully you noticed it as I was making that mistake and you were yelling at me. I just didn't hear you, but now I've corrected it. And so the actual Laplace transform of t is 1 over s squared. Okay? So I apologize for that, but that is the correct answer now. 1 over s squared. The integration by parts has been correct. All right, let's do a couple more. The next one I want to do is the Laplace transform of e to the at, where a is any constant. So e to the at for any constant a. So this one is going to be, again, plug into our definition, integral from 0 to infinity, e to the minus st times e to the at dt, right? Plug in the limit definition now. So this will be the limit as x approaches infinity, integral from 0 to x. I'm going to combine this to say e to the power a minus s. Let's leave it as s minus a and put a minus out front, actually. T dt. Remember, s and a are both constants with respect to the integral. And the reason I wrote it this way is because we've been taking the integral of e to the minus something times t in every example so far, right? So at this point, what we can do is we can make a u substitution, a tiny little change in this, right? So yeah, let's just, it's not even really a u substitution because this is not the variable of the integral, right? This is just a constant. So let's call this thing alpha. All right, and so then we get limit as x approaches infinity, integral from 0 to x of e to the minus alpha t dt. So this integral here we've done in the previous examples, both of them, right? And so we know then that this one is going to be 1 over alpha for, I'm just going to write out the conclusion here because we've done the computation now a couple of times, but 1 over alpha for alpha greater than 0. But of course, alpha is not the correct variable. We need to now plug back in what alpha equals in terms of our substitution here. So this becomes 1 over s minus a for s minus a greater than 0. And at this point, we can just write out our conclusion, right? And so what we get then is that the Laplace transform of e to the at is going to be equal to, it's going to be equal to 1 over s minus a. And in this case, we can write this as for our domain is for s greater than a. We can just solve this for s, right? For s greater than a. So that's the Laplace transform of an exponential e to the at for any constant a. And of course 1 is e to the 0t, so actually everything is consistent here. Okay, I've got one more example for us here, so and then we'll leave this lecture here. This will be the end of our introduction to the Laplace transform. For this one, let's say we have a function u sub k of t. We'll call it u sub k because we're going to call it that later on. But let's say that this function equals 1 for t between 0 and k, and then it's 0 otherwise. So it's 0 everywhere else. So this function, the way that the graph of this function would look is like follows here. So it's going to be from 0 to k, it's going to have a height of 1. And then everywhere else, whoops, actually, I'm going to make this one be less than k. It doesn't really matter for the sake of what we're going to do, but for later on it will matter. So we'll leave it open there, and then it's going to be 0 everywhere else. Okay, obviously it's going to be 0 like that. Okay, open on that side. So this is the graph of our function u sub k of t. And let's try to find the Laplace transform of this function. So the Laplace transform of this u sub k of t follow the same definition, right? It's the integral from 0 to infinity of e to the minus st u sub k of t dt. All right, which again, we plug in our definition. First of all, before we do so, before we plug in the limit definition, let's break up the integral based on our function u sub k. So u sub k, this is going to be the integral from 0 to k of e to the minus st times 1 dt plus the integral from k to infinity of e to the minus st times 0 dt. All right. Obviously, so now we don't even need to worry about the limit definition of the improper integral because this is, the integrand is 0, right? And so if the integrand is 0, it's always 0, then this integral is going to be 0. And so actually all we have to compute is this definite integral from 0 to k of e to the minus st dt. And we know exactly how to do this, right? So this one's negative 1 over s. T goes from 0 to k. That's not exactly right. We don't want to forget the e to the minus st here, right? E to the minus st. And so this time I'll plug it in the right order. So minus 1 over s, e to the minus s times k, or k times s, and then plus 1 over s. And so if we combine all this, what we end up with is 1 minus e to the minus ks over s. And so this is the Laplace transform of a function. This is called a step function that's equal to 1 on a finite interval and then 0 otherwise. So it's equal to 0 elsewhere. Okay, so this will be the Laplace transform of this step function, which I've just defined piecewise up here, is going to be equal to 1 minus e to the k times s. It's minus k times s all over s. And this one is going to be valid for s greater than 0, right? So we weren't worried about a limit here, but s can't be 0, and so therefore s has got to be greater than 0. And so there's the Laplace transform of what we've called the step function here. All right, so this is again an introduction to the Laplace transform. We will use the Laplace transform to solve differential equations starting in the next lecture. We still have to compute some more Laplace transforms, but we will see that there is going to be a table in our text. We just have to make sure that we can compute them by hand if necessary. So take the time during this section to work out these definitions, make sure you can compute the integrals, take it slowly to make sure you get the right answers, don't make mistakes like I did. And I'm going to leave this here. I'll see you guys in the next lecture.